that is my solution. And here, that can give you a little more information. That is the distribution of the grade, and just to let you know where you stand. And this, last time I didn't do this one, but I will try to keep this one kind of give you this kind of information. Okay. My wish is to build up a normal distribution. Okay, and but yeah, that is it's supposed to be in that way, but okay. So that is for chapter 3, and so now we come to our the chapter 4, and that's been for a couple of days. Let me give you a quick review of what we are doing in chapter 4 about bending. The last weekend, I go to the dump site to dump the garbage. I found this. I picked it up. Okay, I think this is perfect. This basically is a beam, and we bend over like this. So basically here I make a line, the upper portion above the line that is in compression, and the lower portion in the line below the line that is in tension, and or opposite, vice versa, like this. Okay, and based upon this one, last time we have come up with is this. And there exists a certain fiber. This fiber won't change in length, won't deform before and after bending. So here we take in the and this bending is bent over like this. And we say this distance, this is the center of the center of the curvature. So measure from the center of the curvature. Here is the rho. Rho is the radius of the curvature of this line. This line is unchanged before and after bending. Okay, that is the features of this bending properties. And from there, last time we have is this. On the cross sections for illustration purpose, and we like to not to draw the distribution of the strain on the curve, but we try to draw on the straight. Okay, so hopefully you understand. So that is this specific fiber. And last time we have come up with is the distributions. For example, if this bending is applied in this way, the distribution of the stress is like this. And for example, if we're interested in this point and say that point, we give a location, y. And at this site, this stress equal to sigma y, rho y, no. Like this, right? Is that right? Is that the one I left from last time? Can you double check that one?
No.
Is that right?
You said sigma, not tau.
Oh yes, sigma. Yes. So this is what we have done from Friday last week. And in this equation is not that useful yet, but this equation provided us a lot of the physical insight to the features of the bending like this. Okay, what kind of features we can read from this equation? The first one is the magnitude of the bending stress is a function of y. So that means the magnitude of the bending stress is a function of his positions from this line. The distance is larger than the stress. The magnitude of the stress is larger. So from here we can readily identify the maximum compressive stress is on the top for this case. The maximum tensile stress for this case at the bottom. Again, those magnitude is in linear proportion to y, and just we indicate in this kind of straight line profile. Okay. Vice versa, if the bending is like this, then the maximum tensile is on the top. So here you can see the location of y is the key parameter to help us to calculate. So right now, the matter of the issue for engineers, futures like you, is you have to determine which location that is most interest to you. Then you determine the y for your calculation. Okay, the formula is here, but I couldn't instruct you to determine what kind of value of y you need to use. But that is the indication. Okay, that's the first one. The second one is this. Y is the distance measured from this fiber. Okay, and this fiber, where exactly is this fiber? The fiber, I say from the beginning so far to here, is the fiber is from located from between the top and the bottom, somewhere in between. And the fiber in specific is determined by this radius rho. Okay, and what is rho? Rho is the radius of the curvature of this fiber. Because we say that for this kind of bending, we assume all the fibers are in concentric, is part of the circular segments. Okay, so basically this rho, if we measure from anywhere to the fiber, they should have the same value. Okay. So to determine the location of the fiber, we have to solve for rho. Because without this location, without the knowledge of this location, you can see here on my drawing is this side, the rho, that fiber is a bit higher, and this side is a bit lower. Depends on the shape of the cross section. I need to engineer my model, so next time you will see a little bit different. So the determination of the position of this fiber, that is critical. Without that position, without that knowledge, we wouldn't be able to precisely measure the y. Okay, and so today we're going to finish this kind of topic by identifying the location of the y, of these fibers. And by the way, what is this fiber called? And before I proceed, I want to give a name. This fiber from here you look at is this line. Actually, this fiber constitute is a plane. The fiber here you see actually is a plane coming through this model, right? Okay, this one in this way, in terms of 3D scenario, we call this called a neutral surface. So again, looking at this in terms of 3D, this line represents the intersection of a specific plane to this side. So basically, this line, the plane constituted by this green line actually is a plane. In solid mechanics, we say that is a neutral surface. Neutral surface is this. All the parallel fibers on the neutral surface is undeformed due to bending. Doesn't matter which kind of bending you do. The green fiber is always remain as its original length. Okay. And on the cross sections, so this is a side view. If we look at the cross section view, for example, let me put it kind of generic. So for example, if the cross section is trapezoidal, here I show the cross section is rectangle. Next time I'm going to cut it a little bit. So here, this is the intersection here. So on the side, the neutral surface intersects with the cross section, we see is this line. So that is this line you see it. And this one in our solid mechanics, this line is called the neutral, N-E-U-T-R, a neutral axis. And again, neutral axis simply is to indicate the line indicating the intersection of the neutral surface to any cross section. And that gives us a line. Okay, that is called the neutral axis. Okay, just the two new terminologies. Okay, and with this one introduced, and then today we're going to work on is to determine the rho. I want to keep this one. So to do this, we have to go to the equilibrium equations. Look at this model. So basically this model is, if you wish, you can redraw this one again. So this is the very long part of the beam. So on the other side, again, this is the pure bending. So on this side, we have the same distributions of the stress, okay, like this. In this model, in this beam, we apply the bending like this. So bending is like this. The bending is the only external loading we apply, nothing else, right? So we have this. So the externally applied bending induces such deformation. That means the externally applied bending induces certain internal reaction. That reaction causes such deformation. So in terms of the force equilibrium, externally applied loading, which is bending, must be in balance with all the internal reactions, right? So we take for example, say, let me define this is the XY coordinate system. X-axis is horizontal. So first one, we take the equilibrium equation in the axial, in the horizontal direction is equal to 0. We see what happens. So this point, let me get this one. So this is a point. So let me say this is the, again, this is a side view. I should keep this one. So this point corresponding to the side, the cross-sectional view is this area. This area, let me call dA. Okay, so okay, if you wish, you can call this is dy. So now on the entire cross-section, I want to find out what is the total force. And right now in this section, you see is this view, okay? So that means right now the beam is in this way. So this is the axial direction. Right now I'm taking up is the equilibrium in this direction. And equilibrium equation in this direction, that means the summation of the stress over the area. So that means we take up is the stress, and we do the multiply with the dA. This represents is the small force due to that reaction on this strip. And I take up the area integral on the cross section. So this represents is the total reaction force in the axial direction. This represent is the total reaction, and then it's emphasize this is reaction force in the axial, in the longitudinal. How about that? So right now I'm doing is, right now I take the summation of all the stresses. For this case, on the top is compression, and the bottom is in tension. But here I take the summation, take the area integral of all the stresses over this cross section, and like this. Okay. And this is the total reaction force in the axial longitudinal direction. Do we apply any external force in this direction? What kind of loading we discuss here? Bending, pure bending. So that means in this direction, do we apply any force? No. So what would be this term? 0. Okay. The second equation, we take the moment. We take the moment equilibrium equal to 0 here. And now for this case, and again, this is the distance y. So right now, in a similar way, all the forces applied to this is equivalent to the dA. So dF. So that means the sigma multiplied with dA, that represent is a small force. Small force applied on this small strip. And that strip is has a distance y from the neutral axis. For this line, or equivalent to this, for this small point, that is a small force. Small force multiplied with the y, basically that is, in this view, this small force will produce a bending that is bending over inside. Or on the other side, we look at this point. This point represents is the location of the small force, that is sigma multiplied with dA. And that small force pointing to this direction. And the small force multiplied with this distance, actually this will produce a bending in this direction, right? Might be okay? And you can see the same thing, doesn't matter where we pick the locations, the bending always has a tendency in that direction. Even at the bottom here, so if we pick this point, this is a small force, and that has a tendency to produce a bending in that direction as well. So that means if we multiply this small force with a y, and we do the surface integral again on the cross sections, those will produce the net bending in this direction, right? Okay, and this is the internal reaction torque, or no, reaction bending that is produced from the external bending. And what is the external bending we apply? This one, right? The magnitude m is given. M is a constant. M, if you remember in the very beginning, I showed you a slide, at Olympic, they lift the weight, right? And I told you that in any portion between his arms, that is in the constant bending with a certain magnitude, right? So that is the magnitude we are given. So here the M is our given magnitude. Here is the given constant. So with the two equations, we can begin to solve for the informations. So for the first one, and cross section, and CS represent is a cross section. Okay. And we simply introduce this cross section. Sigma, we have already the sigma expression here, so that is minus E rho times y dA equal to 0.